All right, folks, picking up here, I forgot to put a nanometer there. So what is this going to be of the order of? This is going to be like 40 something picometer, plus that, you end up with 44, whatever. So lambda coming in is about 40, whatever, 41.2 picometers. Picometer is, nanometer is 10 to the power minus 9 meters, and a picometer is 10 to the power minus 12 meters. So 1 picometer or 1 nanometer is 1,000 picometers. Okay? So when you do this calculation, you end up with something like 0.0004 nanometers, okay? Which is, 0.04 nanometers, ends up being about 40 picometers, plus what you get here gives you the lambda prime. Always lambda prime minus lambda. For the last part, I just want to talk quantitatively about the hydrogen atom. And this was another development, Bohr model of the atom. And a key concept in there is also related to quantization. So we really don't know, in the end, guys, what electrons do around a nucleus. You have a nucleus, whatever. In the hydrogen model of the atom, you just get a photon in the middle, and you have an electron orbiting, right? So you have this positive center, and we liken it to the electron sitting in orbits. It really doesn't do that, right? But the electron is sitting here, wants to go there, sitting there or there. So when an electron, the key thing about quantum mechanics is the following. One of the key things is the electron is sitting here, wants to jump to, it doesn't really look like that. But the only way for the electron to jump up to that level, so you have level of energy, let's say E2 or E and E prime, okay? For the electron to go from here to there, it will have to absorb a photon such that the energy of the photon, hc over lambda, must be exactly E prime minus E, delta E, okay? So if it is a little more, a little less, won't happen. That's quantum, right? So it might be that the photon coming in has enough energy to take us from here to there, or from here to there, and there we can play games like that, right? Yeah, you can say there is multiple levels and energy in electron in ground state, going to first excited state, so on and so forth. But the idea is that the electron will not jump from here to there, unless there's a photon coming in with the exact energy that it needs to do so. And an electron will only jump from here to there, from higher to lower, when it emits a photon such that hc over lambda for the photon is equal to the difference in energy levels. Right? The expression for the hydrogen atom is there are quantum numbers that we're not going to look at, of course. Actually, I want to leave it at this point. I want to trouble you with the quantitative part. I've done enough in the course. Folks, this is what I bid you farewell. I was really happy to be able to say goodbye to you in person. You do your best to, we're going to be very considerate in the way we do the grades, but you still have to do the work. I know the intervenous videos are a lot, but they're short, so please keep that in mind. They're not for the whole course, they're for that week, maybe a week and a little bit. And then you have diffraction, and you have, modern physics. So expect a question on geometrical optics, two lenses maybe, and another question with a mirror, and something like spherical refracting surface. Expect a question that has to do with interference, and a question to do with diffraction, and a question, so 5 questions, let's say. Expect a question that has to do with some modern physics as well. And you might include the hydrogen atom. You can look at the Bohr model of the atom and look at the energy levels, ground state versus excited state. There is a neat formula you can use, negative 13.6 divided by n squared for the energy, and then it's sitting in an energy well. So, it's the ground state is, the lowest state you can have, and you can rise from there. N is equal to 1 gives you the ground state energy. Again, I'm just saying that to you as we covered it. The one thing we have not covered in the course is the derivation of the double slit interference diffraction intensity and the single slit diffraction intensity, which is not going to be covered on the exam. It is done in the nose for you, and you can look it up. It won't be part of the exam though. I wish you all the best. It was my privilege and joy to have most of you, right? To have most of you, to have you all. I'm just kidding. To have everybody, it was a blast. It was a great class. You guys are an amazing class. It was the most fun I've had in a long time. I've had you for 2 terms, and I feel count myself very lucky. Sorry things had to be cut short. I hope you all stay safe, and as much as possible active and in good spirits, and bring good spirits to people around you. When this is over, all said and done, come and you can buy me a coffee or something, and we'll talk about increasing your market fee or something. Okay. Okay. Have a good quarantine, and I wish you all the best. Bye bye.